All right, we are ready for notes 1B and 1C, which talk mainly about models. And near the end of this, we'll get into measurements and converting between metric units. So we're going to use models. Remember, models represent. They're not the actual object. They're representations that allow us to see or learn a little bit about what the real object looks like. And this class is very mathematical, as you're going to find out, starting as we get to the end of notes 1C. So are we ready to begin? Why do we use models? Well, we can't always look at the actual object. In fact, have you ever seen the Earth? No, not all at one time, but we have things like globes. You'll see a picture of one in just a little bit. Globes will help us learn things about the Earth. Here's your definition of a model. A workable explanation. Because we can work with or we can learn from looking at various models. Models will help us to explain and describe an event or a phenomenon or an object. You've seen models of atoms. That model's much larger than the actual atom. Most models are actually much smaller than the actual object. Think of a model airplane or a model car. Models are representations. Again, usually much smaller than the object, but occasionally much larger, such as in a model of an atom. They're never the actual objects, though. Models are only representations. In theory, a model will explain a relationship between two or more phenomena. This is your definition of a theory. An explanation of a relationship. The thing about theory is there is no actual proof that theories are correct. We just believe that theories are likely to be true, but there's no way to prove. And in many instances, theories can end up being shown to be false. But there's your definition of a theory, a model that explains a relationship between two or more phenomena. A law, this is something that we deal with a lot in physics. A law has been tested so many times that we know that laws are going to be true. They've never been shown false. And one thing about laws, many of them, not all, but many of them involve math, as you're about to see. Usually have a mathematical formula, and one of the formulas that we're going to talk about later on in the year is Newton's second law of motion. Force equals mass times acceleration. And we're going to hit that a lot as we get into the physics chapters later on in the year. Ready? Here on the right side, you see some pictures of models. Okay, let me come over here. We have a model of an atom right here. I don't write well. My handwriting is not the best. Here's a model airplane. And when I was a kid, many kids loved to put model airplanes together. We can learn things by looking at a model. Here's a globe. Let's try to make that a better looking G right here. In a globe, we might be able to learn the shape of a certain continent, such as North America. In an airplane, now there was a time when you were very little, you didn't know much of anything about airplanes. But now we can see possibly the shape of a common style of airplane and maybe how many engines this plane has. In the model of an atom, this is carbon, and we'll learn that these dots represent electrons. We can see that carbon has 6 electrons. And if the red represents protons, you'll see there are 6 of those as well. And if the blue represents neutrons, you'll see that most carbon atoms have 6 neutrons. So we can learn a lot from models just by looking at even a picture, such as that carbon model, or an actual model. We do have an actual globe in the classroom. A physical model, these are things that we can actually see and touch. We can't see and touch atoms, but we get the results of them. We can see and touch the models very easily. Models show what objects look like, such as the atoms, the airplanes, and the globes, or how things behave. Now later on, we'll talk about sound waves and light waves. Gases, that's actually our next chapter, and more about gases later on in the year. And energy, we'll talk about different kinds of energy and the models that go along with how energy transforms from one kind into another. Conceptual models, they explain ideas. Okay? So you can kind of link these two words together. A concept is an idea. So conceptual models talk about ideas, such as worldviews, ideal systems. Now these are very likely opinionated because ideas don't always come to fruition as true facts. Concepts are just ideas and we learn a lot of facts about them. Mathematical models include equations like I showed you a moment ago. Force equals mass times acceleration, and virtual representations. Many laws use mathematical models. Weight equals mass times gravity. Momentum equals mass times velocity. These are mathematical models that many physics laws use. Ready? Oh, I forgot. I wrote that a little while ago, but there you see it typed on the screen. Force equals mass times acceleration, disregarding friction, of course. Now, ready. Models, though, do have their limits. When we saw that model airplane, we can't see inside the cockpit and all the little controls on the control panel. We can't see everything about the atom and that model of the atom we had a little while ago. We can't see quarks and other subatomic particles. That model showed only protons, neutrons, and electrons. Models can change over time because we learn more. The periodic table is a model. The periodic table represents, right now, 118 known elements. Didn't start off that way. Started off with only a handful and took many decades and centuries even to come up to the 118 that we now know of. And that's because scientists kept learning more and more and more. And even about that single carbon atom model, more and more got learned, and when you get into high levels of physics and chemistry, you'll see even much more complicated models of carbon atoms. Valid models are true for the time that they are made. So we consider these models valid for now, but as more information gets discovered and learned, then models can be changed over time, such as that periodic table. Again, it took many decades and even a couple of centuries to build up to the 118 known elements. So models do have their limitations. We can't learn everything about the object, but we can learn quite a bit. Ready? What's the goal of a model? To teach us information. We need our models to be workable. Here's that word again, workability. Be able to modify as new information occurs, and we've mentioned the periodic table of the elements a few times already. That's a workable model, and who knows, maybe more elements will get discovered or generated in nuclear facilities sometime in the future. Many of the elements, especially near the end of that chart, were synthetically made in nuclear reactors. They don't occur naturally. So more information got discovered, got learned, and got used to generate more atoms. And we'll talk very basically about that process at another time. The workable model, though, still has to meet these two criteria. One, the model has to explain and describe the scientist's observations. The model has to be able to teach us something if the model's to be useful. What else besides the shape of the continents can we learn by looking at a globe? We can learn the comparative sizes of each continent, where the continents are, and many of them are divided into the countries, the size of the oceans. Some globes will even show us the other set of north and south poles that many people don't realize, the magnetic north and the magnetic south poles. So for a model to be useful, the model must be workable, must be able to teach us some information. And the models need to be accurate. A flat map of the world is not as accurate as a globe is, because a globe is rounded. You'll see on a flat map, a lot of the land masses have been distorted to fill in gaps that would be there. You look at the globe and compare, well, then you have different shapes for countries such as Greenland, up where the top of the globe really starts to come together, but it's much flattened out on the map and has to be filled in. So the globe would be a much more accurate model of the world than a flat map would be. So workable, needs to explain and describe, let us learn from, and the models need to be accurate. Well, if they're inaccurate, they're not worth using. Ready? What's the goal of model? Well, look at these two models here of the universe. You'll see on the top, the Earth is placed in the center because at some point in the past, people believed that the Earth was the center of the universe. Of course, as more information became known, we now know that the sun is the center of our galaxy. I said universe a moment ago, but many people believe the Earth was the center of the universe and the galaxy, and now we know that the sun is, and then we see the planets surrounding the sun. So what's the goal? Get us the most accurate information that we can at the time. Here's an example of workability, information that's been changed as new information became available. Geocentric, and notice what I did with the colors. The blue geocentric matching the blue Earth in the model. That was a past belief, but as people learned more and more about the planets in the galaxy, people learned that the sun is the center of the galaxy and the planets revolve around the sun. That's called heliocentric. Helio means sun. Geo usually refers to the Earth. Of course, centric being the center. As we learn more about the galaxy, the model changed. And now we use the heliocentric model, knowing that the sun, the most massive body in our galaxy, is the center, and that's the reason the planets orbit the sun. Ready? Scientific inquiry. Here, I'll use a different word that you might be a little bit more familiar with. Scientific method. A process used to solve problems. It's called by both. But the chapter in the book says inquiry, so that's what we're going to use. What is scientific inquiry? That is a process used to solve complex problems. We can use the scientific method or scientific inquiry to solve pretty much any problem, even a daily problem, such as how to get to school on time. Knowing more than one way to go, well, what if the one way we like the most is blocked? Traffic jam, tree falling down on the road. We need to know another way. We use a scientific method by testing different ways to get to school, even between the buildings here, so we're on time to class. If one hallway is way too crowded, we'll go a different hallway or maybe even walk along the sides of the buildings. Use that process to figure out the best way to get to class on time. Scientific inquiry is, here's a word we said before, cyclical, a cycle. Continuing the process and repeating the process in the experimentation. Because unless the experiment takes many years to complete, we want to do the experiment multiple times to make sure of accuracy. The scientific method, but inquiry just means we're going to keep on repeating the process. But this is scientific inquiry. The key words here are to solve complex problems. Ready? Here are the steps. Observation. Look around. What information do we already know before we begin the process? Questions. What do we want to learn now? Based on the information I already know, what do I want to try to figure out? Do some research. Try to learn more information to see if we already have an answer to the question or if that question needs further examination. Hypothesis. Make a prediction. What do we think will happen? So you take your question, how can I get to class on time? And you turn that into a complete sentence. If I use the less crowded hallway, I can get to class on time. Investigation. Try going through that less crowded hallway. But you want to do this multiple times because maybe this one time there's a reason that hallway is empty and it's usually more crowded. But if you do that from first period to second period every day for a week, then you get the idea that this hallway may be a better path to get to my class. Analysis. Now you found all your information. What does all this information mean? If I walk down the center hallway, that hallway is a lot more crowded. That makes things a lot harder for me to get through and get to class on time. If I take one of the other hallways, those hallways are less crowded. That makes easier for me to get to class on time. Make your conclusion. Taking hallway C or walking outside the buildings will help me to get to class on time. And remember, we want complete sentences here as well. Go ahead and fill that up. Tell you about communication in a moment. Obviously, you want your question here. You want a complete sentence here. And you want a complete sentence here when you make your report. And then communicate. Remember, we do experiments for ourselves, but even better when those experiments and those solutions help other people, which is glorifying to God. So you want your friends to get to class on time so they don't get tardy slips and get demerits and things. Well, maybe you can help them out. That's a good thing. You communicate. You let other people know what you have learned. Ready? All right, now, start getting a little bit mathematical here. What is a measurement? Measurement, what do you think of when you see the word measurement? These things tell us the size of some quantity. They're going to involve both a number and a unit. And I'm emphasizing unit. In this class, to get full credit, you have to give me the correct units in your answers. See, 6 feet is far different than 6 meters. So if you give me an incorrect unit, you've actually given me a wrong answer. 6 meters is more than 18 feet tall. We have to make sure that we label, put the correct units on our answers. One more. 50 miles per hour is a much different speed than 50 kilometers per hour. These are not equal. A mile is more than 1.5 times longer than a kilometer. So we have to make sure we use the correct units in our answers. 2 types of data that will come about when we do scientific processes. Scientific inquiry, or scientific method, if you will. Qualitative. These are descriptions that do not use number. Color. The cup is blue. Size. I'd like a large soda, please. Shape. Home plate is shaped like a pentagon. These are qualitative descriptions. Color, size, and shape are probably the most commonly used qualitative pieces of data. But as soon as I put a number to my measurement or data, I now have what's called quantitative. Now, you've heard the word quantity quite a bit. Quantity is an amount, which is a number. So quantitative data are numbers, often used as measurements. I just gave you some examples a little while ago. 50 miles per hour, 25 kilometers per hour, 6 meters per second. The mass of the object is 10 kilograms. We have a number, and if we have a measurement, we also have a unit. And again, we must put correct units in our answers. Here are a few more examples. 5 meters, this is a distance. 25 kilograms is mass. 12 meters per second is a speed. Now, if I say 12 meters per second north, then I now call that measurement a velocity, and that's coming at a later time, the difference between speed and velocity. Ready? Here's a fancy term with a simple meaning. Sistema Internacional. Of course, I'm sure I botched that pronunciation. That's a fancy term for metric system. And there's your abbreviation, Sistemi International. Okay, so it's actually kind of backwards. Many languages put the noun first and then the adjective. This is a worldwide system of measurements. It's very consistent. We're the only country in the world that uses feet, inches, yards, and miles consistently. Pounds, ounces, gallons, and things like that. We're the only country in the world that does that. Makes it harder to communicate with other countries. All the world uses the metric system, and little by little, America is becoming more and more metric because it's much easier to communicate because this is a worldwide, very consistent system. Here are some very common metric units. A kilogram, which measures mass. The meter measures length. A liter measures liquid and gas volume, fluids. Liquids and gases are fluids. The Newton measures weight and force. You've heard of kilogram, meter, and liter. I don't know how much you know about newtons already, but that's something we're going to talk about in physics. Weight and force. Very different from a pound. I weigh about 220 pounds. Multiply that by 4.44. Now I weigh about 880 newtons, which is a very, very different unit. Almost all metric units, except for time, we'll come back to that in a moment, are based on multiples of 10. 10 decimeters. Well, actually, I said that wrong. A decimeter is 10 meters. Then a hectometer is 100 meters, so that's a multiple of 10. A kilometer or a kilometer is 1,000 meters, multiples of 10. You see on the screen? Look on page 16. Giga, that's a billion, a multiple of 10. Mega means million. Kilo means 1,000. Deci means 10. Then you get to your base unit, a meter. Then you have centimeter, 100th of a meter. Millimeter, 1,000th of a meter. And especially in computer terminology, you're talking about micro and megas and nanos. The size of an atom is measured in nanometers, billionths of a meter. Those are just a few of the commonly used metric units. There are many, many more. Now, about time here. Time is considered both English and metric. And the basic unit is the second. But there are 60 seconds in a minute. There are 60 minutes in an hour. And here's something you might want to know. Because of that, 60 seconds in a minute and 60 minutes in an hour, that means there are 3,600 seconds in 1 hour. That cancels, that cancels. 60 times 60 is 3,600. This is a number you're probably going to want to memorize if you haven't already. Ready? Measurements, though, have limits. When I put that ruler up against the pencil, can I be absolutely certain that I have the edge of that pencil perfectly lined up with the edge of that ruler? Do I have them both perfectly parallel to each other? Or is maybe the pencil kind of spread out a little bit diagonally like that? So the limit, one of them is, did we set everything up just right? Do I know that the ruler is made perfectly? Even though they may be factory and machine made, that ruler may be flawed. Over time, things happen. Warping happens to the ruler. That's going to change the exact length, especially if that's a wooden ruler. So there are many limitations. Did I read this correctly? Did I read this straight on, or did I read this from a side? Because if I look here and I look straight on, just doing a quick guess now, about 9.5 centimeters. But if I look from this side, that might look more like 9.8 centimeters. So the way we view the instrument is going to change. So we want to look straight perfectly in as we're trying to read measurements. We can't get 100% exact measurements, and I just gave you a few reasons why. Weather conditions may affect certain materials that the measuring instrument is made of. Very hot temperatures, some materials tend to expand just a little bit, and in cooler temperatures, those same materials may contract just a little bit. So they're not exactly the same every time. Now, a couple of definitions here. The word accuracy is how close to the accepted or the expected value did we get. Okay, let's assume no bonus points on the test. Perfect accurate score, 100. We score 98. We're very, very close to the exact perfect score. We say we have a very accurate score. Accuracy is how close to the accepted or the expected value. These terms kind of get interchanged in normal conversation, but scientifically and mathematically speaking, they do have different definitions. Precision is how close to exact we get, and this is based on decimal places. And a great example here is a number you're all familiar with, pi. We tend to use 3.14, especially in middle school math, when we're finding the area, the circumference of a circle. However, that's not the exact value of pi. Hit the pi button on your calculator, assuming I remember these correctly, 15296, and I forget what comes after the 6, but you see that's a much more precise measurement of the value of pi. In fact, this goes on and on and on and on forever and never repeats and never ends. Pi is what we call an irrational number. The bigger your calculator screen, the more digits you might see on there. And if you were to find the definition or the value of pi on a computer, it may go on and on and on and on and on and on and never end. But precision is how close to exact based on the accepted number of decimal place values that we're going to use. So if I take this off, this is normally what we would use. So in this class, instead of using 3.14 when we get to where we need pi, we're going to use the pi button because that will give us a much more precise and a much more accurate value of pi on the calculator, and you'll see that your answers would be slightly different. We must estimate the next place value after the smallest marking on the instrument. So look at the pencil once again. The pencil, we're measuring in centimeters. Okay, this is the English, and this is the metric, the centimeters. And since we're talking about science class, we typically use the metric system. We're looking here, and this is measured in centimeters. We have our whole numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then these small markings, these are millimeters. And we have 10 of those because 10 millimeters make up a centimeter. Now it's time to measure the length of this pencil. And sometimes we'll just kind of look really, okay, about 9.5. But if we're doing experiments that we need the best measurements we can get, we want accuracy and we want precision, we have to look a lot more carefully. So we look and we count up all the little bitty lines and we see that, okay, it looks kind of like right there, so 9.5 centimeters. Now, look at the last rule here. Let me erase this out of the way. How close to exact, that's precision, we must estimate the next place value after the smallest marking. In this case, the smallest marking is 10th, which would be millimeters. But now I look even more carefully. Get this out of the way. I know I'm in the way. I'll get out of the way in a moment. And I look a little more carefully, and I see that the tip of that pencil lead is actually between the 0.5 and the 0.6. So I have to look really carefully and try to estimate how far between. And if I look really carefully, it looks like possibly halfway between the 0.5 and the 0.6. Well, I know for sure that I'm 9 centimeters. And I look carefully and I see that I'm just a little past the 0.5 centimeters. So 9.5, and then I have to estimate the hundredths place. It looks to be about halfway. So I'm going to put a number that looks about halfway. If it looked a little more than halfway, I might put 0.56 or 7. And if it was just barely less than halfway, I might put 9.53 or 9.54. The thing is, once I estimate, I can't go any further because I don't know for sure about this last number. That's definite. That's definite. This is an estimate. Therefore, I cannot go any further. So the best measurement I can give for the length of this pencil, assuming everything else is just right, is 9.55 centimeters. I see ones, I see centimeters easily, I see tenths of a centimeter, so I have to estimate hundredths of a centimeter. Let's finish filling the screen now. The instrument's smallest marking is tenths, so I have to estimate the hundredths, and again, by doing so, I got approximately 9.55 centimeters. Definitely over 9, definitely 9.5, about halfway. So I'm estimating the hundredths. Ready? Now, almost done here. Unit conversion. Let's say we have 5 feet and we want to know how many inches. We want to turn 5 feet into inches. We use something that we're already familiar with. We all know, I don't want equals here, so I'm going to rewrite that. 5 feet. We all know that there are 12 inches in a foot. Need more room here. Just like in math, when we have something like 6 times 3 divided by 3, we know that those will cancel and we're left with the 6. Units do the same thing. The feet will cancel with the feet. Inches is left over. 5 times 12 is 60. Of course, by now you notice, 5 times 12, but this is really how that works. Well, what if the numbers aren't so obvious? We do have unit conversions to keep track of. Use fractions equal to 1. Now realize something. What I had up there a moment ago, 12 over 1 does not equal 1. But 12 inches over 1 foot, since those are the same length, that does equal 1. Any value except 0 divided by itself equals 1. 0 divided by 0 does not exist. 1 kilometer is 1,000 meters, so this fraction equals 1. 1 kilometer over 1,000 meters. Factors will change the units, but not the value. That's like changing a $5 bill into 5 $1 bills. I have the same value. I have $5 worth of money, but I've changed the unit and the appearance. 4 quarters equals $1. Same amount and value of money, but a different unit and a different appearance. So what we're doing when we do conversions, we're changing the units, we're also changing the appearance of the number, but not the value. We will continue and keep the same value. There may be a reason why I want to use one value, one appearance rather, than the other. Just like I may need a reason to have 4 quarters instead of $1. Older vending machines would take quarters only. So I put my dollar bill in the change machine, I get back 4 quarters. I can put 2 quarters into the machine, get my soda. I have 50 cents left. The soda's worth 50 cents. I have the same value in completely different appearances. 2,000 millimeters times 1 meter over 1,000 millimeters equals 2 meters. All right, let's put this up this way so you can see that a little bit more easily. As a fraction, I'm changing 2,000 millimeters into meters. Why would I want to do that? Doesn't really make sense to talk about something being 2,000 millimeters long. 2 meters long makes more sense for the length of your table. Is closer to 2 meters, which is 2,000 millimeters, but it doesn't make sense because of the size of the table. We want to use a unit that would match the size of the object. Now let's write this in fraction form. Since I want to keep meters, I'm going to put the meters on top here. 1 meter over 1,000 millimeters. All right, let's change colors. Notice that the millimeters are going to cancel and the meters are left over. Now I just do the math. 2,000 times 1, which I don't even have to worry about, divided by 1,000. So that gives me 2,000 divided by 1,000. That equals 2. So my answer is 2 meters. They do get more complicated than that. And with practice, which we'll do, you'll get a lot better at it. But the unit I want to keep goes on top. Now, on occasion, I have to change both the top and the bottom unit. I'll show you how in just a moment. But if we're looking at just one conversion factor, what we want to end up with will go on the top. Ready? All right, metric to English. The same process, but rounded off. Okay, this time I'm not going to write on the screen because I already have it typed. 3 kilometers. How many miles is 3 kilometers? Okay, you might sign up for the 5K run. And if you're not familiar with kilometers, you want to know how far that is, you change that to miles. 5 kilometers is approximately 3.1 miles. So what about 3 kilometers changed to miles? 1 mile is approximately 1.6 kilometers. Now that is not exact, that's a rounded off value. And there really can't get perfect exact matches when we go between metric and English because we don't have an exact value of 1 mile to 1.6 whatever kilometers. Okay, so we use the 1.6. That means 3 kilometers is approximately 1.875 miles. Now, how does that happen? Look on the right. 3 kilometers times a fraction equal to 1, so we'll change the appearance in the unit, but not the value. Now, look what happens here. The kilometers end up canceling, and we're left with miles. Now I just have to do the math. 3 times 1, which I don't care about, but if that's a different number, I do, and then divided by 1.6. Approximately 1.875 miles, and we have to put the correct unit in our answer. So once again, very quickly, and we're almost done, just a tiny bit left. The kilometers cancel, I'm left with mile, and I just do the math. 3 divided by 1.6, and here's my answer. And we'll do some practice problems. All right, let's look at the last page. Everything's already up there, so I'll just go through it. 153 meters per second to kilometers per hour. Okay, we're more familiar with kilometers per hour because it's closer to miles per hour. So 153 meters per second. I want to get a color that's going to show up and contrast with the color you see there. Here's where we start, 153 meters per second. Now we're going to use some things that we already know. We know that there are 1,000 meters in a kilometer. We know that there are 3,600 seconds in an hour. I want to end up with kilometers and hours. Kilometers on top and hours on bottom. So I have to match these up. If I flip the fractions over, I'm going to get wrong answers. The way I do this, and again, we'll do some practice problems. By knowing that a kilometer is 1,000 meters and set up with kilometers on top, because my answer wants kilometers on top, the meters are going to cancel. Well, that doesn't get us to kilometers per hour yet. That just gets us to kilometers per second now. So now I need to change seconds into hours, and I want my hours on bottom. That means I want these seconds to cancel. There are 3,600 seconds in 1 hour. So now seconds are gone, and hours is left on bottom where I want that. Now I just do the math. I don't have to worry about ones. That's the good thing about multiplying and dividing by 1. We don't have to. So it's 153 times 3,600, and then divided by 1,000. Do that math, here's what we get. 550,800 kilometers over 1,000 hours, and then do the division by 1,000, and here's what we end up with. 550.8 kilometers per hour is your final answer. And you check everything, and quickly one more time. Meters cancel, seconds cancel, we're left with kilometers over hours, and then we just do the math. And that's how we do unit conversions. Ready? All right, we are done with this lesson. Hope I modeled this lesson well. represented it well for you. We will do practice problems with the math. Thank you.